and then this. Uh, this one, this one. No, no, no. This is not a good one. So maybe I can use this one. This reading. Uh, this one. And then the presentation mode, like this. Correct. It's beautiful. And the writing and everything is okay. Okay, what about sound? 5 second latency. No, it's okay. I think it is. What? It was there. It was there just a little while ago. Okay, this one. Look at this. No, I think it is look okay. I think it is okay. So if you've been wondering why my face is so big, that's simply because I lost this extension cable between my computer and the camera. So that's why the camera needs to be so close to me. So my apology. My apology that my face is too big. So what you can do is that while you look in my videos, you can put something blocking the lower left corner of the slides or video, so then I'm not bothering you. Okay, let me just take this off. Yep, like this. Okay, what's going to happen today is that we will get started by explaining uh, what's going to happen next week, because the next week is a special week, is an exam week. So we have a midterm exam, and how the midterm exam will be organized. That where we're going to get started, and because Mustafa and Suraj are so pleasant guy. I'm not, but these guys are so nice. They propose to me that can we be relaxed and can we try to serve our customers, yeah, students as well as possible, and make it this exam in a way that is open a 1 full week time. I was very much against, like, no, 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 I don't want that. So I want to have an oral exam in one particular time. I want to make your life miserable and all that. But they were fighting back, and eventually they convinced me to go in a way that we have a written exam open a 1 full week. That's going to be next week. And you have 5 questions, and each of the questions you already know. So those are the ones that are introduced in a slide. There will be nothing outside of those questions that I already mentioned. And what are those questions? Okay, now I need to scroll down seriously. There's going to be, you need to close your eyes because you are not allowed to see what's happened in class quizzes and so on and so forth. Don't look, don't look. Close your eyes. Close your eyes. No, they cannot. Okay, there. Online exam consists of 5 questions. So out of these, so we have a total of 20 something questions. 5 will be selected for you. 5 will be randomly selected for you. So it's going to be something that if you're following what is your fellow student doing, you will not possibly get the same questions to yourself. So it's a lottery based, and you never know. But the way you can practice yourself is this exam is that please take a look at the questions, all the questions. And then there is this instruction that some of these questions are more important than others. So we will actually, yeah, see you later, Mustafa. So we will try to emphasize those more important ones. So the chances that you will see those more important questions will be higher than these lower ranked questions. But be prepared to answer all the questions because you never know how the lottery goes in your case. So you have a 2 hours time. What do you think? Is 2 hours enough? What do you think, Sura? So it could be 3 hours. Yeah, we can make it 3 hours. 3 hours. Okay, 3 hours, and then that's it. You have a full week time to do it, so it will be open Monday morning 0:05, and it will be closed on Sunday at just before the midnight. Just before the midnight, and I think it is a high risk to start doing the exam just before the midnight. So make at least 3 hours. Start at least 3 hours before, because I'm not sure how it is behaving. Even if it allows you to open it, maybe it closes at midnight. I don't know that, and I don't. It closes at midnight. Okay, all right. So Surat just mentioned that even if you started at 11 p.m., then you just have a 1 hour time to do the exam, and everything will be closed and submitted automatically, but not recommended to do so. So try to do that well advanced. And this time you only have one attempt, so just a one attempt. But the questions are not so bad because you know each of them. And as mentioned earlier, so you actually have this opportunity to take one question out from many. So the list will be available for you right after this lecture, and there will be a voting action, and we're collecting the votes. So your opinion matters, like always in a voting. And based on your feedback, we're going to take one question out, and we will let you know which question will be taken out. And there will be one question that will be there for 100% certainty. So that another thing you need to vote. So please vote about the question you hate, question you love. And we will do the math, and we will let you know which is the question that will be in an exam paper for 100% certainty, and which one will not be there, again, in 100% certainty. How that sounds? Oh, this voting action. Okay, the voting is already there. Voting is there. Now it's all about how far we can go today, because I'm hoping that we can cover 110 slides today, and we can cover all kind of things today. Unlike, because I always have these big dreams, big plans in my head, and then I come here and I started to discuss about Malaysia and weather and stuff like that, and I forget about polynomial expansions and safe functions, and then I realize, oh my God, I haven't explained about the safe functions, but I've been more about carrier counseling and stuff like that, and then we need to act accordingly. So we need to see how far we can go here. All right. Okay, so one more thing. So this voting action will be closed on Thursday at midnight. So yeah, Friday you're gonna get an email when you see, okay, this question will be there. Okay, now, if you wanna just pass the course, make sure that you can absolutely answer the question that will be there for 100% certainty, because that already gives you, 6 points. 6 points is not yet enough to pass the course, but it's a good start, really good start. Rest can be kind of okay, and you will be okay in the exam too. Yep. This is we are easygoing guys in LUT University, but there's one exception, and that's a plagiarism. Plagiarism is a serious crime. This is something that never ever goes away from your life. So there's a murder and plagiarism. You commit the murder, it will haunt you rest of your life. Plagiarism, same thing. Seriously, that's going to happen to because most probably you end up to be one of those big shot politics, big politics like prime minister or something. Then the journalists will come to LUT University and they want to see each one of the papers you have ever filled in your life, and they're monitoring if there's any plagiarism, and if they found one, you need to step down in your prime minister office. Very unfortunate. So it hunts you down rest of your life. Every night you woke up in the middle of the night, oh my God, I made that plagiarism. It comes after me. And you see my face like I'm coming. That's a nightmare, serious one. So don't do it. You do whatever you want, but no plagiarism. And what we do when we see the plagiarism, when Suraj sees the plagiarism, we are not the ones that are dealing with. So we are not. We don't care about. We don't want to hear your explanation because I'm sure they are great. We just couldn't care less. It goes automatically to curriculum head. Curriculum head automatically send the report to rector. Automatic. So this is automatic thing. So don't play with the fire, please. And sure, you have a good explanation, but we just don't care. Same thing than in a murder. I'm sure there's a good reason to commit the murder, but we don't care. Oh, then we're going back. Don't look. Don't look. Don't look. All right. So there's a lot of things to cover today, and for sure we cannot cover them all, but hopefully at least something. Okay, this is where we are at. So I'm going to close the explanation about. So thank you, Suraj. So I'm going to close the explanation about finite element modeling, and I just need to see what are the comments from online participants. Okay, no real comments. So we're going to close the case about the finite element modeling, and then we're going to start looking the ways we can reduce the size of a finite element model, a finite element model. And that will be based on the model reduction. So we're going to move from one space, which is called nodal space, nodal degrees of freedom, to another space, which is called modal degrees of freedom. Can you recognize the difference? Nodal, modal. Or is it like, because I have an accent, so maybe it's not so clear. So can you recognize nodal, modal? Because they're completely different story. All right, and that is related to this eigenvalue analysis and model reduction technique. It's something that is a really, really important piece of information that I would like to explain to you. But prior to that, what we looked a week ago was three-dimensional multi-body system dynamics. And we discussed about the inertia forces that consist of a mass matrix and quadratic velocity vector. And something we found out to be useful was that the inertia tensor, that is this guy here, can be mapped to any rotational parameters you want by using this magic T matrix. So even if you decided to use 4 rotational parameters, that's okay. There is no need to express the inertia properties using these 4 parameters, but you can use a body reference coordinate system, and that's what helps your life a lot. And then once you get the inertia tensor, that can be mapped to any set of unknowns you want with help of the T matrix. That's it. That's the message that I would like to deliver. And this is the details of the inertia tensor. So mass moment of inertia, mass product of inertia, so not big surprises there. We also discussed about the lamp mass approach, which is a kind of way to describe flexible bodies, but kind of only. And kind of only because what's by the way happening to this guy here? You see the same that I do, or am I just tired? You see the same. Okay, very good. Okay, all right. So this technique about lamp mass approach is an extension from rigid bodies. So what you do in this approach is that you take one single rigid body, you divide your rigid body to a number of rigid bodies. Between these rigid bodies, you're going to introduce the spring elements. And that's going to be your way to model flexible bodies. Problem is this numerical stiffness. And numerical stiffness means that there are high frequencies and low frequencies simultaneously in one model. And remember what's the problem there? The problem is this. Because the last time I was unable to make any drawings, so I'm going to make this drawing to you. So if you think about that, there is a force with a high frequency acting like this. And the response will be a combination of bending and axial direction. You agree with that? axial direction, the high frequency is much higher than the bending direction, particularly if I'm going to make this structure to be very long and slender like this, all right? And then I'm going to have a component here and component here. Now, what's going to happen to the response is this. This is time, and this is my response. Let's say that this is a displacement u here, which is a combination on x and y. So the response looks like this. But if you take a close look about the response, you take this line here, you look at closely what happens here, and you make a magnification like this back here. You see how is I need to make a magnification here because I'm blocking the view. So this is this magnification. You look at the response, it's like this. High frequencies, which is not important for us, typically not important for us. But the integration scheme recognizes immediately, hey, wait a minute, there's something high frequency happening in my model, and it tunes its steps to make sure that it can capture something that we actually don't care at all. We don't care about this. But the time step will be minimized or will be very small because of this behavior, and then the computation becomes to be slow. That's a problem, and that's where you have this. If you make a line where this is a frequencies, there are low frequencies, but like the one that is related to bending, and high frequencies that are related to axial deformation. Same model. That's a problem. Okay, numerical stiffness. Finite element model. Finite element is something like shown here. So these are the plate elements that are getting close to each other, plate structures that are getting close to each other, and then they will bounce away from each other. Good example about how is a finite element model. So it's looking like a fishing net, or something that consists of Lego pieces. That could be another way to look how is a finite element method. Each of these Lego pieces is an element. Elements are connected together in nodes, in nodal locations. Nodal locations are the one that we are able to solve. So we are able to solve displacement at the nodal locations. So that's what we do in a finite element modeling. But before we're able to do that, we need to know how is a life between these nodal locations. That's what the finite element modeling is all about. So life between these points. And how that can be estimated? Well, easiest, it can be estimated by using a polynomial expansion. Polynomial, which is based on the number of degrees of freedom and the type of the element you're dealing with. Now, we'll look at this funny spring element. This is very much in a move, very much in a motion. So online participant, I just need to let you know that our projector is not doing well and is vibrating quite a bit, particularly in the upper right corner. Yeah, not in a lower corner, but upper corner. All right, so spring element that we looked last week consists of two nodes. And because it's two nodes, each of the nodes can move only in this axial direction, so we have a total of 2 degrees of freedom, because plus and minus, but it's still 1 degree of freedom. Plus and minus is not different degrees of freedom. Now, because this system has a 2 degrees of freedom, so we can express displacement within the nodes. Now, within the nodes, this is the key component here by using polynomial expansion like shown here. We could use this polynomial as it is to solve unknowns that are this A0 and A1, but they don't carry any clear physical interpretation. So that's why it's better to replace these unknowns by nodal degrees of freedom, because they're representing something that is very much understandable. All right. While we do that, we get something that is called safe function. Safe function, hear me this. Safe functions are explaining you what is the way that the element can deform. That's what it's telling you. So it's like, what are the inherent capabilities of element? So this is what it can do, and nothing else, absolutely nothing else. So let's say that there is one element. I'm not going to explain this. You got this thing, so you understand that what it means, right? Okay, so I'm not going to explain that any further. Now, what it means in the case of this spring element, it means that, if you introduce the displacement to one end, the other nodes are following using this linear path, linear curve. This is not very illustrative because it's a kind of like planar representation. Even this is a line representation. But let's say that if originally your element is having this length and you compress that to be this length, this tells you how these particles between the endpoints are moving. That's what it's doing for you. All right, and then now using this information, we can construct a stiffness matrix, and that came with the help of this kinematic matrix that defines the relationship between the strain and displacement. And that's it. Very mechanical. Rest is very mechanical. Only thing where you need to do a little bit of thinking is polynomial expansion. Everything after that, mechanical. Nothing else. No thinking, doing. Okay. All right. And then we can get the stiffness matrix and external applied forces. So this is elastic forces, stiffness multiplied by displacement. And this is externally applied forces that is divided to this nodal degrees of freedom, because force 2 need to be expressed in terms of nodal degrees of freedom. Why? Because this equation, the unknowns are nodal degrees of freedom, so that's why. You need to make them match. Of course, in reality, they could be distributed forces, and distributed forces are accounted by using these volume integrals and shape functions, how the forces are divided. Now, what we do in the finite element modeling is we're solving this guy by inverting stiffness matrix and multiplying external applied forces with inverted stiffness matrix. Then we can get these displacement, but because we also have these shape functions, we can tell how is each point of the structure, how they are behaving, how they are moving, how is their displacement. But typically, only nodal degrees of freedom are displayed. But when you think about the stresses, when you printed out the stresses and strains, you actually need to know each particles in your system. And that's when you're using, again, these shape function matrices. Okay, that's it. Pretty clear. Okay, let's take a look at another example. So I have here a beam element. Now, beam element that consists of a total of 4 degrees of freedom. And now I'm looking at the displacement only in transverse direction. The only displacement in the v direction, this direction, nothing else. I have degrees of freedom such that this point here, there is a displacement in a global y direction, v direction, that is noted here. Then there is a rotation in the same point and same degrees of freedom in another end. So a total of 4 degrees of freedom. 4 degrees of freedom. And now, because it's all about how the displacement is in this direction, this transverse direction, I can use a polynomial expansion with the 4 unknowns. How can I select it? I'm going to take myself back in this Pascal's triangle, and I'm going to select the components in a way that I'm going to take this A0, A1, and rest I can select however I want. I can take it in a line, or I can skip some of them and make a non-conforming element. That's all is possible. But you just need to know that the fused element is still converging, because some of these non-conforming elements are not converging the right solution, which is making them hard to, well, they have no use then, of course. Okay, now this is all about the center line. So we're describing the center line all the time. But at the same time, we also know where each of the particles that are off from the center line, how they're behaving. So if I have center line here, I always know that particles off from the center line will be perpendicular with center line. And this is the type of the element that is called Bernoulli beam element. Bernoulli beam element is unable to take transverse shear deformation into account. Transverse shear deformation is somewhat important, particularly if you have thick structures that you would like to analyze. And this assumption that that cross-section always remain perpendicular, this is unable to capture the transverse shear deformation. You know this story already. Okay, meaning that if I have here cross section like this is again perpendicular. Four arrow off, I go with the cross this center line, more bending strains I'm gonna get. So my bending and transverse deformation are combined like this. So they are simple. So it's like a partial differentiation. It's telling you how is an angle here. And the angle is like this tangential angle here. And something perpendicular to that is a cross section. Simple like this. Okay? All right, so here's my polynomial expansion. I have here a0 all the way to a3, and a3 is multiplied by x power 3. Look what I did. I took this directly from the Pascal's triangle with no skipping. I took each of the component as they are in a Pascal's triangle. All right. I'm expressing that by using these polynomials and unknown coefficients. Now, coefficients are something that I'm replacing by not a degrees of freedom. How can I do it? I could do it by introducing the information that I have, and that's the information where the nodes are located. So once I introduce this information, I get a total of 4 equations. How many unknowns I have? 4. So this is solvable. So I can extract the information like this. This is this previous equation, but this time expressed by using matrices and vectors, right? I'm gonna take this guy in the middle, will invert it, and I can solve this guy. And that's exactly what I did here. And the final thing is the substitution, which after which this is how the shape functions look like. Now the shape functions have this special feature that they are orthogonal. That means that they are not a combination of each other, but they are independent bodies. Independent bodies in a way that if I first of all take a look at this shape functions that is representing what happens if I introduce the displacement in a y direction. You know, look at that. So I'm introducing the displacement in a y direction. Keep in mind what are the rest of the 3 degrees of freedom. So there are rotation. Rotation here is 0. Displacement, displace is 0, as is a rotation. So no other degrees of freedom is imposed or is non-zero other than the one where the shape functions is affecting to you. Nothing else. So we okay. Very good, very good. So I wasn't sure. But we are okay. You're with me. Okay, good. All right. And then this is a rotation. So when I introduce the rotation, displacement here is 0. Rotation here is 0, as is a displacement. And same for the other end. So that's how it goes. All right. Now, what if not taking polynomial components as they are listed in a Pascal's triangle, but I'm simply going to skip some of them? How this will make my life different? It will make my life different in a way that how I'm predicting these particles to move between these nodal points. That's exactly what it's doing for you. And now, if you're not happy with the polynomials, like I explained earlier, you can take something else, because eventually what we need is something that is capable to be independent from the rest of the modes, the rest of the ways that the element can deform, and just showing you the way that the deformation can take place. So maybe trigonometric functions can do it for you. Maybe these NURBS, these non-rational uniform, non-uniform B-splines can do it for you. So you can take something else too. But most commonly used are still polynomials. Why? Because they're so nicely representing small piece of the problem. And again, remember what we're doing here. We are not solving the entire structure, but very small piece of it. Nothing else. All right. Now, how it's going to be different? So I'm going to take this polynomial where this component is mandatory, this is a mandatory, and then instead of having this x power 2, I have x power 3, and then the final component is x power 5. You see that the behavior is different. Which one is better? That is hard to tell. This is non-confirming element. And like I say, sometimes this non-confirming element have this ability to have a faster convergence. And the convergence again means this, that if you have, let's say, a cantilever beam here, well, this is so simple example that this is not very good. But let's say that there is very, very complicated loading case, something bending and this and that, and that the final displacement is complicated like this. And then I have here number of elements and my correct displacement. So it means like how fast I can reach the correct solution. That's what the convergence means. Now this is an inherent feature of the finite element method. So you're getting closer, closer, and closer to actual solution, but never necessary one-to-one match. So when you look at the 10th digit, that may be a little bit off, but who cares? What difference it makes? It makes no difference. So it's not necessarily absolutely correct, but it's a very, very good estimation. That's the nature of the finite element method. And it's get better estimation, more element you have. And that's what is how fast you can get the good estimation is called convergence rate. Good convergence rate means that the low number of elements is able to produce very accurate results. And why this is important? Because then you can save some computational power. Okay. Then in a finite element, this is off topic. And I don't know why I'm explaining this to you, but I'm still will. So, in a finite element community, this displacement-based finite element community, what we are looking at the moment, so where the unknowns are displacement. There are many other type of finite elements where the unknowns are not displacement, but pressures or something else, which we are not going to take a look at here. But this displacement-based finite element method, there are two ways we can do this convergence. We can either improve or we can increase the number of elements, like I explained it. So you put more smaller and smaller elements to fill it the same structure, you get the better and better solution. Or you can increase the order of your element. The order of the element means that you're adding maybe internal nodes to your element, you're adding more complicated degrees of freedom to your structure. So it means that if I have originally this kind of the beam element, instead of having nodes in the end, I can add one extra node here, one extra node here. This makes this element to perform better, but with the cost of computational efficiency, because you understand that now I have more unknowns, because now it's no longer this point and this point, but two additional points that are in the middle. So this is called HMP refinement. HMP refinement is the two alternatives: increasing the elements or increasing the complexity within the elements. Usually, when you use a commercial finite element method, it's all about increasing the number of elements. But now you know that there is this alternative. So you can show off next time you discuss with I don't know. Okay, so this, for comparison's sake, this is how they look different. So these are the shape functions. Again, finite element method is all about this. Nothing but how is a life between the nodes, nothing else. Now, once we know the life between the nodes, then using this mechanical computing, we can get stiffness matrix and we can get the mass matrix. Makes sense? Comments, questions? All makes sense. Always. So you knew this already a million years ago, more or less. Okay, what about our finite element people? You were aware of these P and H refinements. You knew that too. You knew that too. You're lying. You knew that. More or less. Okay, very nice. Very nice. What about the mixed finite element when there's a displacement and pressures simultaneously unknowns? Yes, sir. Correct. Newton method or Gaussian elimination method. So where exactly? I think at where you using this nodal matrices or so what exactly you do with your Newton method? Polynomials. Okay, that's completely new to me. So polynomials. Okay, now I'm not sure where you gonna get this information. Okay, who was the teacher? Ah, yeah, yeah, I know the guy. Yeah, so he's using a Newton iteration. Ah, okay, okay. I got it. I got it. So that I think is very educational. So you see this nature that is approximate method. Approximate method is not an exact method. So it's incorrect to say here's the solution because it comes from the finite-element method. You can say that this is a very good estimate of the solution because it comes from the finite-element method. And computer simulation could be correct, could be, but not necessarily. Keep this all the time in your mind. So there's a chance that is correct, but there's a big chance that is incorrect. Which one to trust? That's your engineering sense. This Pasi, by the way, is a good teacher. Yes. So when using lump mass approaches, when what was your question? Rest of your question? Yeah. So why did he reducing the size of the model? Because lamp masses are never introduced to rotational degrees of freedom. That's going to be something that needs a further explanation, but rotational degrees of freedom are ignored. Ignored. That's why when you use a lamp masses and when you use a beam elements in a lamp masses, they're in a straight line. They don't have this rotational inertia. So if you take a hold of this beam structure and you rotate it like this, it's going to go crazy because there is a missing inertia. The spinning speed will be velocity of light, which is not realistic. So because it's simply because it's missing rotational inertia. So rotational degrees of freedom are ignored. But well, this is it's a translational degrees of freedom. You are not introducing any inertia whatsoever in that method. But there are other ways, there are alternatives to express it. So that's why. Okay, physical interpretation of safe functions. Would you like to discuss about this, or this is all clear? Remember what we discussed about what is that is doing for you, what that is describing for you. Not saying any further, but B defines the rotation of the particle. You know that is a joke we have. Joke defines the strength displacement relationship. No clear interpretation. Is it on or is it not yet on? It's on. Okay, very good. Okay, so we'll get back to that momentarily. You see the in-class quiz. Team Malaysia voting for no votes. You passed the vote. We voting because this is ultra democracy in this classroom. We all are forced to vote. D, meaning no clear interpretation. Okay, so Team Malaysia thinks no clear interpretation. All right, so we're moving on, and I will get momentarily back to that. Okay, now a short story. I'm going to speed up a bit because, as I said, the finite-element method is all about these polynomials. The rest is mechanical. What is mechanical is this, that we're going to find a relation between these, how is this displacement outside of this midline. And that, of course, is this cross section and how far off you go from the cross section. That's why the y is there. Further off you will be from the cross section, the bigger is your displacement. Now, using this information, I can express the relation between the strain and displacement. And my relation is this. So I need to just differentiate my shape functions twice with respect to length. So remember, this is my angle. This is how far off I go from the cross section. Using this information, I can take my previous slide and substitute that to here, and that's how I'm going to get this equation. This is my strain displacement relationship. But again, no thinking needed really, because this is very mechanical. Now you get this B, which is a kinematic matrix. And once you have a kinematic matrix, you can get the stiffness matrix. Please do not think, just do it. Okay, this is the one way you can construct your mass matrix, alternative for your lab masses. Now I'm distributing my stiffness, my inertia, using density here, and my shape functions, because the shape functions, again, is dividing things within these particles between the nodal locations, okay? So I'm using my density and my shape functions, and I'm getting something that is called consistent mass matrix. It's not the diagonal, as is the case of lamp mass matrices, but the full representation. And now I have actually inertia components that are related to rotation too. Not very accurate, but still something. Okay, now, should we go, let me see. Okay, let me explain this, and then we're going to take a look at the in-class quiz, right? Very good, very good. Any other comments, questions? Okay, how is my speed today? Too slow, too fast, too average? Very good, okay. All right, now, remember where we started. We started from the polynomial expansion. So then we were able to get the stiffness matrix and the mass matrix. And then once we have the entire structure, we can combine these element stiffness matrices to system stiffness matrix. This is, by the way, something that I need to show you a slide next week, how you do it. But basically, you're overlapping your degrees of freedom in your system stiffness matrix. Meaning that, shortly, I'm going to explain it to you. So if you have a spring element, two spring elements, this is element number 1. This is element number 2. Each of them has a 2x2 stiffness matrix. And obviously, this system consists of 3 degrees of freedom, like this. So how you can construct from, this is 2x2, this is 2x2. How you can construct the system matrix that is 3x3? By overlapping them. And the overlapping will be something like this. So there is going to be this submatrix, which is 2x2. And the submatrix, which will be 2x2. And they're overlapping here. So they're sharing the degrees of freedom in the location that they're actually sharing the degrees of freedom in physical life too. That's here. So these components will be summing up here. And that's how you can construct the entire stiffness matrix for your system. Remember what we did in a multi-body system dynamics was a block diagonal representation. And it was like if there would be 2x2 matrix, that will be constructed another 2x2 matrix in a way that they never shared any degrees of freedom whatsoever, but they have this block diagonal representation. Here, they are overlapping. And because this overlapping, I'm going to have this one joint node, that is sharing, that is between the node, the element 1 and element 2. That's how the finite element method works. All right. You can do the same for the stiffness matrix, and this is how you can extract your external applied forces, and this is it. That's it. Now you're ready to, this is your equation of motion for a flexible body that is described by using finite element method. So what you can do then is that you can solve this guy here, which is an acceleration, as shown here. And then you can integrate from Acceleration, you can integrate velocity, and for velocity, you can integrate position. And that's what we were after, okay? But there is a big problem here. The big problem is this, that the typical finite element model consists of thousands, tens of thousands, hundreds of thousands degrees of freedom. And that's not good because this equation needs to be solved every single time step. And time step we're using in a multi-body system dynamics is a millisecond or 10 milliseconds. Sometimes it's 10 milliseconds, but often it's a 1 millisecond. That's going to be too much computing. So we just cannot do that. So we need to do something else. And we need to reduce the size of our finite element problem by moving from nodal degrees of freedom to modal degrees of freedom. Modal. All right. That's what's going to happen next. All right, here is a same story explained. This is not the good way to go because this is obviously too much computing for us. Too much computing for us, particularly when we look at the reference motion, rigid body motion. If we cut the corners, it's described by using 6 variables. 6 variables. And now suddenly we have 6 plus 100,000. They don't match. They don't get along. One is too big. The one too big we need to make it smaller, and that's going to be our mission. So we are in a mission, and our mission is to make finite element model to be smaller, to make it comparable with 6 unknowns that we're using in multi-body system dynamics. 3 unknowns if it is a planar case. Okay? And what we're going to do is this magic. So we're moving from one space to another space, and something that comes with V is assumed deformation modes. So how we are assuming not just the one element anymore, but the entire structure to behave. This entire structure behavior are expressed by using this matrix here. So the matrix consists of columns. Each of these columns are representing numerically one possible deformation way. One possible deformation, which is not a single element, but each of the nodal degrees of freedom, each of the elements in your system, meaning the entire structure. How much that is affecting your solution, this deformation mode, that's going to be our new unknown, which is called modal coordinates. I'm going to explain this again in a second, but finite element model consisting of 10 degrees of freedom. That means that there's 10 different ways that the finite element model can deform. All right? So those are the different ways. If we keep these ways in this computing, we lose nothing. But some of these ways may not be important for us, particularly if you think about the finite element model that consists of 100,000 degrees of freedom. How many different ways the structure can deform then? That's 100,000. Maybe all of these 100,000 ways is not equally important, but some of them are more important than others. And now we just need to find the king. We need to find the king and the queen. Once we know the king and the queen and their child, their family, we need to look at them and leave the rest of the crowd with no attention. That's not democracy. But this is ultra opposite to democracy. Okay, you're following my reasoning here. So we need to find the most valuable ones and leave rest with no attention whatsoever. We actually kick them out from the game. When they kick them out from the game, we've reduced the problem size. Okay, that's what we're going to do. So here's questions, and then I'm going to explain this same story a little bit a different way. Physical interpretation of eigenvector. This is the way that the structure can deform. Way, not an absolute deformation, just the way that it can deform. Physical interpretation of eigenvalue, that is a natural frequency, in shortly speaking. You know, what are the natural frequencies of the structure and corresponding deformation? Because structure modeled by using 100,000 degrees of freedom will consist of 100,000 eigenvalues and corresponding eigenvectors. 100,000 natural frequencies and 100,000 ways that the structure can deform. Not all of them are important, generally speaking. Okay, how to conduct the eigenvalue analysis. Maybe we can have a time to look at that. Mass normalization of eigenvectors, I don't think so, but we'll see. We'll see. Okay, is it okay we have no break today? Can you handle me? Okay. Okay. Let me try to explain this whole story about the modal decrease of freedom one more time. This is a cantilever structure. And this cantilever structure is modeled by using these finite element beam elements that we looked a little while ago. So each of these nodes that are black in a color consist of 2 degrees of freedom. This is 2 degrees of freedom in a sense that there is a displacement in this direction and rotation, except that there is not. And why not? Because this node is here connected to ground. So the degrees of freedom are taken away. So this is not possible deformation. But then comes next. This guy has a deformation this direction and rotation, as this one, and as this one, and this one. So there's a 1, 2, 3, 4, 5 nodes, other than the boundary nodes. Each of them has a 2 degrees of freedom. So how many degrees of freedom in total? 10. 10 degrees of freedom. 10 degrees of freedom, and each of these 10 degrees of freedom means something. They means how the one single point within the structure will deform. All right? How we can get these 10 unknowns, so we can get these in a way that we're solving finite element solution, static solution like this. So these 10 unknowns are these guys, these nodes. All right? So we're solving this equation by inverting the stiffness matrix. So we get each of these points, how they performing, how they moving and translating. So it's going to look like something like this. All right. What we can do, instead of looking these points, and now we really get these 10 unknowns. So this vector will consist of 10 components. So what we could do instead is that we can actually make an assumption that most probably the way the structure can deform will be the lowest, how it is rotating or how it is vibrating in this lowest natural frequency. In the lowest natural frequency, it is deforming like this, something like this, something like that. But how much like that? I don't know. But what if I do the following trick? So I'm describing this mode, this deformation mode numerically. That's the way that I'm explaining how much this node is moving this direction, how much it is rotating, how much this mode is moving this direction. It is rotated relatively, just relatively with respect to each other, but not absolutely. Something that I have here, vector that is also consists of 10 components. Each of them are representing these nodal degrees of freedom. But numerical values are not absolute, but just the way the structure can deform. I can make this to be absolute number by multiplying this by something that is called amplification. How much this particular deformation mode is affecting to my life. This is called P1. And now instead of having these 10 unknowns to be unknown, my P, which is my kind of my amplification, will be my unknown. Makes sense? Because what I can do then is that I can multiply by, because this, of course, this whole story, if I put it in like this, one mode, deformation mode multiplied by one multiplication, that's going to be vector of nodal degrees of freedom. So meaning that I can move from this nodal degrees of freedom or modal space to modal space with help of the assumed deformation mode. That's what I'm going to do. So then later I can use these guys to be my unknowns. And now if I look at, my structure, I can have 10 of these. Now this was ID number 1, this is ID number 2, It goes all the way to ID number 10. But maybe this 10 is something that I can ignore without significant loss of accuracy. That's exactly what I'm about to do here. So I'm going to select the ones that are contributing the most valuable players, most valuable player. You know, that's what they call in NHL. So I'm picking up the most valuable players from each of the teams, and I'm ignoring the rest. I don't care about the rest. Okay, that's what I'm doing. How can I get these deformation modes? I can get these deformation modes from a eigenvalue analysis. Eigenvalue analysis is not an absolute value, but is a way the structure can deform. It is highlighting me the ways the structure can deform, nothing else. You know this. Okay, how can I conduct a eigenvalue analysis for a finite element model? Well, first of all, the first thing that I need to do is that I need to ignore external applied forces, because this is not about the responses. This is about how is an inherent feature of the structure, not response. Feature. Not response, a feature. Okay? You know that eigenvalue is all about the relation between stiffness and mass. Stiffness and mass. And those are the two pieces of information that I have here. I have here my inertial forces and my elastic forces. My mass and stiffness. Now, for math, I know that the solution for this problem can be expressed like this. I don't know where the heck this is coming from, and I'm not planning to try to find it out for you. But if you want to go through yourself, so you know where that is coming from. Okay, this is the Euler method. So this is what you learned from Pasi. Bachelor level. Okay, so this is this is a solution for this problem. This problem. So once I substitute that solution for this problem, it reads like this. Now I got the new components. Well, the components are not new because they came in this solution here. What I have here is still my stiffness, my mass, and something that is called omega power 2. That's going to be my eigenvalue. Natural frequency would be the easiest way to describe what this is. And hold on. And then this one, which is how is the deformation in this natural frequency? So there's each of the structure in reality and in computation, they have natural frequencies and the corresponding deformation modes. All right, that's exactly what I have here. And now using this eigenvalue analysis, I can first get these eigenvalues. They will be equally many eigenvalues than the degrees of freedom. And there will be equally many eigenvectors, which is a deformation mode, as the number of degrees of freedom. Okay, let's take a look at the animations and then we get back to this. You know these stories. These are these YouTube videos about simply supported beams. 1 degrees of freedom system. So in the 1 degrees of freedom system, how many natural frequencies you're going to find? 1. How many corresponding deformation modes? 1. So it's like this. Simple like this. So 1 deformation mode, 1 frequency. If you have 2 masses, how many frequencies you're going to find? 2. How many different modes? 2. This is your 2 system. This is the first way it can deform. Second way it can deform will be showing you momentarily. It's, where is it now? This is slow video. There. Okay, 3 degrees of freedom, how many different ways it can deform? Not 5, no, that was incorrect. You said 5? Israel, that's not 5. You said 5, it's not 5. It's 3, of course. Sorry that I'm making jokes about you. Okay, so 3, this is the first way. How many other ways? 2 more ways. Okay, simple like this. And this natural frequency That means that if you excite your structure using the same frequency, the natural frequency, your structure will go crazy. It will start vibrating like no limit, but there will be a limit. Like every system, they have a physical limit too, but mathematically, the response will go to infinite in longer time perspective. So it's going to vibrate here to moon and back, and then soon it's going to be more. But that's not going to happen in a real life because there's always some limitations in real life. These are the most. These are the natural frequencies. So the structure is moving such the way that I'm increasing the motion of the platform here slowly. And I'm increasing. What's going to happen first is that the structure that is the most slender, that is the one that is in the right side, started to vibrate because I'm going to hit its natural frequency. And the vibration goes crazy. Okay, this is a kind of slow video. I guess that these are these Feng Shui videos because they're so slow that you can practice your mental strength. Oh, here, finally. Look at the guy in right. He's going crazy. Why? No, the one in the middle, I don't know where we are at. No, I think it is still the right side that is going crazy because we're exciting the platform using its natural frequency. Now look at that. So it's going absolutely crazy where others are moving nowhere because of the natural frequency. That's the eigenvalue analysis. So we can first find it out. These guys. No, look at that. So this is the first eigenvalues, then eigenvectors. Makes sense. All right, so then the second one will go equally crazy, but soon this will calm down because we're gonna go away from the natural frequency. Look, so it started to calm down, that the second one go crazy. Okay, and so on and so forth. So, right, so let me take myself back here. Now, this eigenvalue analysis is gonna give you equally amount of eigenvalues and eigenvectors that the number of nodal degrees of freedom, the number of unknowns, not more, not less. In the maximum case, usually you don't really are not interested in all of them, but maximum number will be the number of nodal degrees of freedom, unknowns. Okay, with that, here's my question to you. I have here a finite element model that consists of m number of elements, n degrees of freedom. Modes, or the model can be used to solve how many eigenvalues, how many different natural frequencies. So is it going to be not equal than the number of elements, equal than the number of nodal degrees of freedom? These two numbers are subtract from each other. These two numbers are added to each other. So which one is correct? What the team Malaysia is saying. Okay, team Malaysia is saying B. Okay. So it's not open. Okay, physical interpretation of shape functions. Can you see? Hold on, you don't see you see nothing. Okay, how can I duplicate? Okay, you see this now? Yep, okay. Success rate competition. 18, 80. No, okay. So there is you serious, 80%. Oh, I can write this, 80%. I'm guessing 95, 90. Okay, what about 100? No. Okay, success rate is this one. Ah. Okay, very low, very low. Major disappointment. disappointment because of the two reasons. Strain displacement relationship is kind of related to that, but it's not what we are after here. So it's defining the way the element can differ because it can use in other purposes too. For example, in distributing the inertia properties. Okay, so I admit that this C is kind of okay, but no points. No points. Okay, the next one. Next one. Finite element model shown below consists of m number of elements, n degrees of freedom. Model can be used to solve n question mark number of eigenvalues. Question mark is element, nodal degrees of freedom, element minus nodal degrees of freedom, element plus nodal degrees of freedom. And Team Malaysia saying B. B. And success rate. Yes, yes, sir. It's going to be no, no. It's going to be 100. It will be 70. No, not no, absolutely not. So it's not going to be that low. So it's going to be. So I can go a little bit down. So 85, 95, 95. No, I'm going to stay in my 100%. 100%. 100%. And last time we got 19 students, so this time we got 18 answers already. So I think we are okay. So you already answered. Team Malaysia was saying B, which is correct. No, no, it's more because no, it's more because Team Malaysia is worth of 20%. 20 plus 80 isn't that 100. That's 100%. That's my math. Okay. All right. So then taking myself back here. Oh, now you don't see this. Hold on. Okay, that this looks good. All right, then I need to show you something. So this is a finite element models that are describing a tube roll. And of course, when we started to look at the natural frequencies and the corresponding deformation modes, the lowest ones look like this. So they look like banana and something obvious. But soon when we started to look this one here, pay attention to this guy here, which is a frequency here. Now the frequency is 200 hertz. So most of the modes are still important. They still are making contribution to dynamics. But as soon as we're increasing the natural frequency, the deformation modes becomes to be more and more exotic. So soon they will be so exotic that you see that their role to responses may not be very important anymore. Of course, we're still in not so high frequencies. We're still in 350 something hertz, so it's not that great yet. But more we're going in this video, the higher frequencies we're gonna meet, more complicated deformation mode we're gonna meet. And some of them are no longer important. And that's the whole trick about the modal reduction. Now, the ones that are very detailed, very exotic, we simply ignore them. We simply do not care about these exotic ones. We only want to see the most valuable players and nothing else. This is already disabled, and the frequency becomes to be 500 hertz. Okay, let me show you even more, something more exotic. These are the simple beam structure, which is a low frequencies for sure. They are important. This makes sense to keep this in your model, as is the case of this one. This maybe not if the loading is not in transverse direction, but when you go with the high frequencies, when you look at the frequency, that this frequency is at 2,700 hertz, maybe again you can still keep it there, but then this kind of deformation mode, which is almost 12,000 hertz, how you can introduce the vibration like this? Yeah, with magnet, but nothing, no other things can introduce the deformation like this. How much you think that it will affect the entire response? Nothing. I mean that I cannot say nothing because it affect, but maybe the digit that is, if I make a number solution, the digital is somewhere close to the wall, maybe that is something that this number is affecting, but nowhere else, nowhere else. And that's exactly what we do in the model reduction method. And then comes something beautiful. Many people actually, by the way, when they learn this, they started to cry. Like emotions are so high that, and it's very understandable because this is a big magic in mechanical engineering. And the big magic is this, that these modes that we're looking at, this, if I'm going to write it like this, plus, and so on, all the way to, I don't know, n, like this. I'm going to construct a matrix, which is the matrix. That's the way that these modes are there. This is the first row, second row, third row, and so on and so forth. And I'm ignore some of them. These columns here are orthogonal with respect to each other, particularly if you're going to get this deformation from the eigenvalue analysis, because the eigenvalue is a magic analysis where these eigenvalues and these deformation modes are orthogonal. They are similar kind of thing that what we learned from the safe functions. Safe functions are orthogonal with respect to each other, as are these deformation modes. And now because of this orthogonality, they have a beautiful feature. And the beautiful feature is such that if you're going to move from your nodal space to your modal space, and you simply substitute that information here, so first it's going to be like mass. Look, this is what I'm substituting here. This is the first part of my equation. And then this is a force. And then I multiply this by transpose because these two need to be expressed by modal degrees of freedom. It's going to be like this. Sorry that my handwriting is not very solid. Like shown here, this one here. And now when you look at these matrices that are, oh, this, by the way, there is this one missing here. When you look at them, they are diagonal representation, meaning that now these modal coordinates are independent with respect to each other. They have no relation, meaning that you can take any one of them and solve it without knowing anything from the others. So that's another beautiful, beautiful feature. That's because they are orthogonal. That's because they're coming from the eigenvalue analysis. But you're not crying. You don't find this to be emotional. You don't find to be this as a big moment in your life. Of course, this is no comparable when you learn to create the equation of motion based on multi-body system dynamics, but still pretty good. What do you say? You say nothing. Okay. All right. Okay, let's practice this. So I have here eigenvalue analysis that I'm going to conduct the structure that is shown here. This is this famous element we learned a week ago. So this is element which is only capable to move, or the nodes are capable to move left and right. So I'm modeling the structure that consists of 1, 2, 3 spring elements. And there are nodes that are 1, 2, 3, 4, 4 of them. And I'm going to conduct an eigenvalue analysis for this structure. First thing to do is that I'm going to take my 2 by 2 matrices. I'm going to construct them to system matrix like it is shown here. This is going to be my first element, my second element, which is connected to neighboring elements, and my third element. And I'm doing the same for the mass matrix. And now I have the components that I need. So I have my mass, I have my inertia. And I do this, I know that you don't do this in a real life, but I wanted to show like how you do it if you solve it analytically. Real life, you're using iterative processes, like you learned in a finite element class. But I don't do that here because I want to show the exact numbers for you. Okay, here is my stiffness. This is my mass. And look at this is what I called earlier was omega power 2. So this is now called as a lambda. And I'm setting this equation to be equal to 0. And I'm taking determinant out of this part of the equation. When I do that, I'm going to get the fourth order polynomial like the one that is shown here. I know that it's a fourth order because, look, there's a lambda here multiplied by this one, and this one. So it will be a fourth order polynomial. And I'm using my symbolic math tool to solve where this polynomial goes to 0. And it goes to 0 in 4 different places that are lambda equal to 0, lambda equal to 12, lambda equal to 60, and lambda equal to 120. And these numbers are related to natural frequencies. So these are the natural frequencies of the structure. Number 0 means what? What this means is number 0? Guess. You can guess. It's not vibrating, correct. But what it means, what it look like. It's not vibrating, but seriously, you're saying rigid body mode. I've been asking this like at least I don't know how many classes every year in, year out. Every year I'm asking this question. People are like, no idea. Never ever they say rigid body mode. What's wrong with you people? So you said correctly. Oh, this is serious. This is very, very serious. How you knew that? Because machine dynamics. Okay, so last time, I think at the timing was different, so you were not participating. Jussi Sopanen explained this to you. So Jussi is guilty. Ah, okay, good. So it wasn't you, but Jussi. Makes sense. Okay, now I'm more relaxed. Okay, all right, this is rigid body mode. All right, then what's going to happen next is I'm going to take one at a time of these natural frequencies. I'm going to substitute them to this equation. I'm going to solve this vector, which is this eigenvector, the way the structure can deform. Lowest is the number 12. You don't need to care what that means. And when I substitute the number 12 to this equation, I can get this set of equations. So I have 4 equations, 4 unknowns. When I'm solving the unknowns, they look like this. Now, something extremely important to understand. This is not a response any kind. Why? Because the equation that I'm solving is this. This is my equation. To solve the responses, you need to know feature of the structure, which is this one here, and forces. But remember what I did in the beginning, I set the forces to be equal to 0. So I don't care about the forces because I only wanted to see the feature of the structure. Now this number or this set of numbers can be multiplied by any scalar number you want, anything you want, and still it fulfills the equation. I can multiply this by 10, by 100, 1,000, 10,000, doesn't matter. It's still going to fulfill the equation because this is just the way the structure can deform. And this way can be amplified or not. This, by the way, this multiplication is called scaling. Scaling means that you want to get your numbers to be as close as 1 as possible because computers are very good in the number 1 and very bad in any other numbers. I mean, of course, they're okay with the other numbers, but as soon as the number becomes to be very small or very large, they are struggling. So the scaling is one thing that we can do. But this shows that if the structure originally is like this, the deformation means that the first one is moving minus 2 units. So it's moving here. Second one is moving minus 1 unit like this. Then 1 plus, 2 plus. So it's getting bigger. But as I can also multiply that by minus 1. Then it becomes to be smaller. That's my deformation mode. You say that sometimes the lecturing is a hand waving. It can be hand waving big time. Okay. All right. So now comes very important, and I'm putting all my hope to you that you're gonna get this correctly. So the physical interpretation of eigenvector, this deformation mode, is what? Relative displacement of nodal degrees of freedom, meaning relative, meaning that they only show the way the structure can deform. Absolute displacement, meaning that you can use it in your analysis. You can measure what is the response. Strain distribution within the structure, no clear interpretation. One only is correct. Which one? And Team Malaysia is thinking heavily. And so we're going to learn the solution. I need to go. I need to take myself in a Socrates. Where's Socrates here? Okay. Now, relative, absolute. Relative, absolute. There's a big difference. Relative is the way the structure can deform. Absolute is that something that you can use to measure the displacement and something you can use in your reasoning. Strain distribution. No comments. No clear interpretation, no comments either. Oh, you don't see this. Sorry, my mistake. Okay, success rate. Yes, sir, 100%. 100%. So are we playing in the same team or what? It sounds that we becomes to be like almost like friends or something. You know, not allowed in LUT University. Not allowed. 100%. 100%, and it would be beautiful. Okay, 100%, and I'm going to give you, each of you, I'm going to give you one extra point in midterm exam. Correct. You heard me right. You heard me right. So one extra point because, okay, now please communicate with your fellow student, please, and revote if needed. Oh, you cannot. Oh, so it's all gone then. Okay. All right. So what's the success rate here? 100%. Team Malaysia is voting A, B, C, or D. B is incorrect. A is correct. Ah, very good. Okay, no extra points. Sorry about that. Sorry about that. Okay. Okay, let me take myself back here because I need to, where I was. Okay. I was here. Now I can do the same for any other eigenvalue. I can figure out the way the structure deform. I can do that. Not a problem. And like I mentioned earlier, the one thing that I can do is that these vectors can be, these deformation modes can be multiplied by any number you want. And that is something that is called scaling. Better name for that is a normalization. There are typical normalization is called mass normalization, meaning that you wanted to get final mass matrix to be a identity matrix. A matrix where the diagonal components are equal to 0 and off-diagonal components are off zeros. This is scaling. But again, it's something that you can multiply these relative numbers by anything you want. Anything you want. All right, so this is a scaling, and I'm scaling my mass to be diagonal and identity matrix. So I'm figuring out what this alpha, that is extra number here, must be, that the solution here is 1. So my unknown is this multiplication number, and I can solve it like I show here. So I can solve it for other numbers too. And when I then do my modes multiplied by original mass matrix multiplied by modes, I'm going to get the identity matrix. So the diagonal components are equal to 0. Off-diagonal components are, the diagonal components are 1s. Off-diagonal components are 0. And then when you do that, then the eigenvalues appears to be diagonal components in your stiffness matrix. And that was my last slide. Then I'm not going to discuss about that, but I'm going to take myself to this one. So here's a summary of the questions. Remember this? Suraj promised that the voting will be on. It's already on. Okay, voted. It's going to be closed, he said, Thursday at midnight. And then we announce you how is the results. But this is the stuff. So these are the questions related to kinematics. I'm not going to read them anymore, but there's 11 questions in total. And there are a little bit about the ranking, which actually makes sense you to focusing on. So the entire kinematics is a worth of 3 stars. 3 stars. Up. Rodriguez equation 5 stars, but there's not that many questions related to that. So it's not so complicated. Mathematical properties of rotation matrix, just 2 stars. Comparison of different methods, 4 stars. Robot kinematics, 4 stars of medium importance. Dynamic Hartenberg is something we learned earlier. Velocity of particle. The only thing is important here is this magic T matrix. All right, how inertia tensor can be related. So this is not so important. 2 stars only. 2 stars. Mass, matrix, and inertia tensor, just the 2 stars. So not particularly important. Equation of motion, not important. But then comes finite element modeling. And finite element modeling is of 4 stars. So it is important. So make sure you understand the basics of finite element modeling. Floating frame reference formulation, the basics. It's going to be the 4 stars. Finite element method, 4 stars. Safe functions, 5 stars. Solution techniques, 5 stars. Modal reduction, 10 million stars. So that's very, very important. Modal reduction. Make sure you master that. Okay. Questions? Craig pumped up was something we were not able to cover. Convergency rate, I think you know all this stuff. Mass normalization. Reference condition was something we did not cover. Everything else. So 24 questions in total. Can you think that you can handle it? 28. Yeah, but it should be 24 only. Because the rest is something, this mode selection, we did not have a time to cover this. Oh, we did. We did. This 26 was okay. This is not okay. 27 is off. This 28 is off. Okay. So 20, let me take myself back here. 25th plus 26th. So 25 questions in total. Now in the voting there may be more because Suraj was not aware that I'm so slow. That's why. Okay. Here it is. Here comes the most important thing. Can-do attitude. Can-do attitude. That's why this Euler or Newtons or other big names are not so important for us, but Elvis, because the can-do attitude. That's more important and more valuable than any of the stuff introduced by this big scientist. So follow the attitude of Elvis. Can-do. All right. So do you have a can-do attitude? Can-do. Okay. Let's go back home. And we don't. Yes, sir. Something. Okay. Questions that I'm looking for is that that are fairly short, but don't fall short of spelling out. So you still need to explain everything you know in the subject matter. But I don't care about learning about your summer vacations and summer trip to some places. So focus on the topic, but everything you know in this particular subject matter. That would be good. And sometimes I think it would make sense if you can make a hand drawing, take a picture of it, and upload it to the system. So handwriting to paper, picture, and do you need to convert that to PDF? I think you do. And then you can put it in the system. Yep. That will be the way to go. but short, still short questions. All right. Can do attitude. Okay, let me see here. Okay, so there, this is still a guessing about the success rate. That game is off. What else? Oh, yeah, I was about to say, I'm not going to be here next week, but I will be, of course, here next week, but no lectures next week. And if I'm right, then we're going to have another schedule in next period, period number 4. So it's no longer from noon to 2, but something else. Can you figure it out? What is something else? Is it from 1 to 3 or okay, look at that. I'm sure you can find it out by yourself. Is what? So is it from 2 to 4 or 1 to 3 or okay. Bicycle dynamics, forget about the bicycle dynamics, no questions from bicycle dynamics this exam. But there will be more visiting lectures and they actually will introduce the questions to next midterm exam. Okay, and have fun. See you not next week, but 2 weeks from now. All right. Hold on. I need to stop this streaming business. Oh, I got 2 likes. 2 people were thumb up. Nice. They got extra points.